Okay, hello everyone. So welcome to the next lecture. So the previous lecture we covered graphs that actually concluded chapter 3. So now we're moving on to chapter 4. And broadly speaking, chapter 4 has to do with functions. And to relate it back to what we were covering in the previous chapter, we're going to look at functions as a special case of relations. And so I'm hoping to get through this quite quickly because I know some of you all are used to functions and the idea of functions. So let's just get right to it. So let's start off with the definition. Okay, a function, sometimes a mapping. Mapping sounds cooler, but function in general. From A to B, right, is a relation. So remember what relation means precisely from the previous chapter. Um, from A to B, such that uh, one, um, the domain of f is A, and second, if xy is an element of the relation f, the function f, and xz is an element of the relation f, then we must have that y equals z. So in particular, what this second condition means is that any element in your domain must be mapped to exactly one element. Um, on a more high level, sort of a higher level than that, if you were to draw a picture of a function, it should pass the vertical line test. That's what the second part here says. Okay? We write f colon a to b to show that a function goes from the set a to b. B is the codomain. Of f. Okay. When a equals b, we say f is a function on a. Okay? And there are no restrictions on the sets a and b as we've used in this definition. They can be numbers, and that's mostly what we'll use our examples on. But they can be things, they can even be sets of sets, ordered pairs, or even sets of functions. You can actually define functions that map functions in a set to some other set, for example, number. Yeah. Okay, so let's just go through this piece by piece. The first part of the definition just says the domain of f is A, meaning like the function maps onto everything in the set A, and then I already explained what the second condition says. So let's just quickly go through an example here. So let A equal the set 1, 2, 3, and B equals 4, 5, 6. Let R1 be a relation on these two sets with 1, 4, 2, 5, 3, 6, and 2, 6. So notice this is not a function. It's just a relation. Why is this not a function? Because 2 is mapped to both 5 and 6 is not equal to 5. R2. Let's say that's 1, 4, 2, 6, and 3, 5. Okay, this is a function from A to B. What should we call R3? Let R3 be the set 1, 5, 2, 5, and 3, 4. Still, this is a function. From A to B. What about R4? Let this be 1, 4. Sorry, let me rewrite that. 1, 4, and 3, 6. Okay, so is this a function? Yes, this is a function. But this is not a function from A to B. i.e., the domain of this function is not equal to A, so we can't say this is a function from A to B. It is a function, just not from A to B. Rather, it's a function from the set 1, 3 to B. Okay, so we just have to be careful when we're specifying domains of functions and what we're calling domains of functions. And B is the codomain, but we can define the following, and this is related to relations. So just another definition here. The range of a function f is equal to the elements in B such that there is a u in A with uv in F. Okay. This notation here at the end here can get kind of tedious sometimes, and so we have a better way of writing it, and this is the way that y'all are used to. So let f be a function from A to B. We write y equals f of x if x and y, xy, the ordered pair xy, is an element of the set of ordered pairs in F. Y is the value of F at x, okay? And x is the preimage of y under F. Okay? So this is some notational, this is just a way to sort of simplify notation. Okay, so let's look at an example now. So let capital F be equal to the set of ordered pairs xy taken from the Cartesian product of the integers with itself, such that y equals x squared, right? So F is a mapping with domain integers, okay? So f of 4 is 16. F of minus 3 is 9. F of, say, something more abstract, t plus 2 is just t plus 2 squared, assuming t is an integer. and f of 10 is 100. What is the preimage? The preimage of 25 is both 5 and minus 5, because we have to think of in terms of the integers. So notice, so maybe let's think about the following. What is the preimage of 7? Now you might be tempted to say it's the square root of 7, but we all know that the square root of 7 is not an integer, and we've defined this function with domain integers. So there is no preimage of 7 under f. So 7 is not in the range of f. What is the range of f? We can just list out some numbers. It's going to be 0, 1, not 2, sorry. 0, 1, 4, 9, 16, dot, 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 so on and so forth. So it's the integer squared. Okay, so now let's look at a little bit more of an abstract example. So example, prove that g, which is a function, actually we have to prove it's a function, but say we have the set of ordered pairs taken from r cross r, such that x equals y cubed. And we want to prove that this is a function from r to r. Now, how do we do that? First, we have to show that, so need to show domain of g equals the real numbers. That's what we want to show, because we want to show it's a function from r to r. And then secondly, we have to show that if xu is in g and xv is in g, then that implies that u equals v. Okay? So proof. First, we're going to show that the domain of g equals r. Now these are sets, and so we know how to prove sets are equal to each other. We have to show that they're subsets of each other. So need to show domain of g is a subset of r, and r, or the real numbers, is a subset of domain g. Okay, so in that spirit, let x be in the domain of g. That means x is the first coordinate in the ordered pairs. X is a first coordinate in the ordered pairs that comprise G. By definition of G, X is a real number. So domain of G is a subset of R. Conversely, let X be a real number. Okay? And now we want to find, we want to show that this is an element of the domain. So then note that the cube root of X is also a real number, because we know that cube roots exist for all real numbers. Thus, there exists a y in the real numbers, namely y equals the cube root of x, for which xy is in G. So x is in domain of G. That is, the domain of G is equal to R. And I know this looks like magic a little bit because it just seems like I wrote a lot just to say very little, but I think it's a good idea for you guys to look through this proof and really think deeply of what I'm doing in each step. Okay, so proof continued. This is the second part. We need to show that f is single valued. So suppose xu and xv are elements in G. Then x equals u cubed and x equals v cubed, which means u cubed equals v cubed, which means u equals v. So G is single valued. Okay, so that's done. Now, so we proved that a given relation was a function. What about if we want to disprove whether or not a relation is a function? Then we need to show that, let's say, for example, I give you a function and I say this function is from the set A to B. You need to find either you need to find an element in A that is not in the domain of F, right? Or you need to show that the function is not single valued. Okay? So for example, so take x squared plus y squared equals 25, right? With domain -5 to 5, subset of the real numbers, right? So sure, you can plug in any number in between these two numbers for x, but this function is multi-valued, because note that 3, 4 and 3 minus 4 satisfy equation. So not function. Okay, because this function is multi-valued. And if you want to see how this relates to the vertical line test, remember I said that the idea that a function is not that a function is multi-valued relates back to failing the vertical line test. We can just draw a circle, and you can see that at let's say 1, 2, 3, if you draw a vertical line at x equals 3, you intersect at 2 points, and so this is not a function. So this is x squared plus y squared equals 25, not a function, right? Okay. So you can say that if you draw a picture and then you say, okay, there's a vertical line that intersects this curve at 2 points, then it's not a function. Now notice sometimes you try to draw a function and it'll look like it's passing the vertical line test, but it might not. So in particular, a vertical line test cannot, so if you say a function passes the vertical line test, that's not sufficient to prove that a relation is a function. You need to prove it rigorously, but it is sufficient to show that a relation is not a function. Okay? So let's look at another example here. So let's take the functions f of x equals x squared and g of x equals x plus 6. Okay. Domain of f equals domain of g equals minus 2, 3. Okay, so it's just those two numbers. And notice that even though these two functions look quite different maybe in your mind, because of the way we've specified the domain, we have the following. F of negative 2 equals 4, which is in fact equal to g of negative 2. And f of 3 equals 9, which in fact is what g of 3 equals. And so the domains of these two functions are equal, and the outputs of these functions are equal, relative to the inputs that we put in. So f equals g. And this gives us the following theorem. Not gives us, but motivates the following theorem. Two functions, f and g, are equal if and only if their domains are equal, okay? And for all x in the domain of either of these, but I'm going to say domain of f of x equals g of x. Okay, and so this is a bit of a not a lengthy proof, but I mean it's not really lengthy at all, but it is a biconditional statement and it is kind of intuitive, so I'm not going to go into the proof. So yeah, I'm just going to leave it at that, and just go right into the next example. So I'm not going to specify domains for the following functions I write down. So let f of x equal x over x, g of x equal 1, and h of x equal the absolute value of x over x. Okay. I'm not going to specify the domains of these functions, but if I give you functions like this and I don't specify them, that means you should think of the largest possible set of real numbers that you can plug into these representations. Okay, so note f does not equal g. Why? Because the domain of f does not equal the domain of g. In particular, the domain of f is equal to the real numbers minus 0. You cannot plug in 0 into the structure of f of x because then the universe is going to explode. And the domain of g is in fact all the real numbers. And so the theorem above tells us that these two functions cannot be equal. Similarly, well, not similarly, but f does not equal h. Well, in this case, the domains are equal, right? The domains are equal, but, sorry, not but. So, why? Because their outputs are not equal. So, for example, f of negative 1 equals 1, but h of negative 1 equals negative 1. And similarly, g does not equal h, because of both reasons, really. Because both conditions fail. And so you have to think about very carefully before you make a statement like two functions are equal. Okay. So now we're just going to look at some examples of functions. Of special functions, I should say. Examples of functions. One is the identity function. So identity function, so let IA be a function from A to A. Then for all little a in set A, the identity function acting on little a is just equal to A. So it just spits out that kind of a function. That it just spits out the element itself. So one of the simplest functions, but yeah, yeah, it's a simple function. Second type of important function is what's called the characteristic function. So characteristic function for set A. So say the universe U is specified, and A is a subset of the universe. Then chi of A from the universe to 0, 1 is specified as follows. X equals the following. 1 if x is in A, and 0 otherwise. In particular, if x is in the universe without A. Okay, so this is a characteristic function. This is called the characteristic function, and you might have seen these in terms of, like, I don't know, piecewise functions, something like this. So a standard example is the Heaviside function. H of x equals 0 for x less than or equal to 0, and 1 for x bigger than 1. So A in this example would be 0 here. X is bigger than 0. So A in this example would be 0 to infinity, and the universe is the real numbers. Okay. And so what does the Heaviside function look like? So here's x. You're going to get, so let's say this is where 0 is, and this is where 1 is. You're going to get a straight line right here, jump right there. So this is h of x. And you can specify the set A to be however you want. If you want 1, if you want the output to be 1 on a very small domain, you can say that I want A to be, say, 0 to 1. And in that case, if A equals 0 to 1 inclusive, then you get something like this. You get Again, let's say this is 0 and this is 1. Get 0 all the way out here, inclusive, and then you have 1 right here. So go from there to there, and then you're back down to 0. Okay. So you can build different functions like this. Three is a more general version of the characteristic function we just talked about, but this is called step function. And without getting too rigorous here, I'm just going to draw a picture of an example of a step function. So let's say -2, -1, 0, 1, 2. So basically you partition your entire set into different subintervals, and then you define a constant value over those subintervals, right? Okay, so this is an example of a step function. Another example is the greatest integer function. What is the greatest integer function? It's an example of a function, so I'm going to call it just the greatest integer function, GIF. Is an example of a function that goes from the real numbers to the integers. Okay, and you assign it the largest integer that is smaller than that real number. So, for example, GIF of 5.9 equals 5. Okay, the book uses sometimes int. So, or int of 5.9 equals 5. Int of the square root of 7 is 2. Int of pi is 3. Okay. Negative numbers can be a little bit more confusing sometimes because you have to think in the backward direction. Int of negative pi is -4 because -4 is the biggest integer that's less than the number I've put into the function. So this is also written as int from R to Z. Five. We also have sequences. These are functions with n as domain, right? The image of n in n is called the nth term of the sequence. Right, so an example of this is say xn, and this is kind of a different notational thing, is we just write x, and then as a subscript we write the term of the sequence. So this is the nth term of a particular sequence. So the nth term is given by 1 over, say, n squared plus 1. Then the image of the sequence would be 1 over 1 squared plus 1, which is 1/2, 1 over 2 squared plus 1, which is 1/5, 1 over 3 squared plus 1, which is 1/10, 1 over 4 squared plus 1, which is 1/17, and so on and so forth. So we have that. Lastly, but not leastly, we have what are called canonical maps. So what is a canonical map? So let X be a set, and let R be an equivalence relation. On X. The canonical map is from X to X mod R. So it maps elements in X to the equivalence class corresponding to that element under the relation. Okay? And I'm going to finish off this section by looking at an interesting example. So let f go from the integers mod 4 to the integers mod 10 with x bar in Z4 being mapped to bracket x in Z10. So notice just the different notation I've used for the equivalence classes in each of these two sets. And consider f of x bar is mapped to 2x. So the equivalence class of x in the integers mod 4 is mapped to twice that element in the integers mod 10. Okay, so if we just write things out, so remember Z4 is going to be just 0, 1, 2, 3. And Z10 is going to be 0, 1, 2, ... all the way up till 9. And remember, each of these are equivalence classes. Equivalence classes. Sorry, I messed up some notation here. So 0, 1, ... up till 9. Okay, so under this mapping, we have that the equivalence class of 0 in the integers mod 4 is mapped to the integers mod 0. Sorry, integers into 0, the equivalence class of 0 in the integers mod 10. F of 1 is mapped to 2, right? The equivalence class of 2. F of 2 is mapped to the equivalence class of 4. F of 3 is mapped to the equivalence class of 6. And so far, so good, right? Now remember, we can think about f of 4 now, even though I haven't listed it up here. If we continue this process, we get f of 4 is equal to 8. But the equivalence class generated by 4 is equal to the equivalence class generated by 0. And f of 0 is 0. And so this function is multi-valued. So defining functions on equivalence relations between, the equivalence relations generated by two different relations can lead to some really interesting results. Okay, so that concludes section 4.1. I hope it went well, and thanks. We'll come back with more lectures next time. Thanks.